Of minutes, not couple of minutes. We're going to start now, and we have the pleasure and the privilege to have with us Professor and my friend Manolis Benis, the new elected president of the University of Ioannina, who's going to be talking about the role and the significance of spin in quantum mechanics. Please, Professor, we thank you.
Okay, good morning, everybody. Always a pleasure to give a talk after the barbecue last night and all this wine drinking, but anyway, I'll try and do my best. As my friend Kostas told you, I am from University of Ioannina, Department of Physics. And for those of you that maybe you don't know where Ioannina is, this is our university. And do I have a laser pointer? No? Okay, doesn't matter. There is Ioannina, in northern Greece. It's a very nice place to live. I don't come from Ioannina, but I lived there the last 15 years. We have a lake. It's very nice to have a lake where you live. And I must say that at night it's even better, especially if you're a young student in the university. You go out on Monday, and all the bars are full. Just give you some hints about your future careers, okay? So, today's talk will be about the spin. It's a very difficult, I think, try to understand what spin is in quantum mechanics. So we'll try to shed some light into this picture. And its role in quantum physics. So first of all, I will start with a simple magnet. I mean, you all know that you can have a permanent magnet, and this will make a magnetic field. This field, you can also create it in another way, by running some current through a wire. Then you have a similar magnetic field, as you can see in this picture, okay? And actually, this field has a magnetic moment, which comes from the product of the current times the area. This you can estimate very, very easily. So we'll take this picture now and take it to the atomic level. Sorry. This is my water. Wow. Okay. So we'll go in this simplistic picture where one electron is spinning around a nucleus. We know that this picture is wrong. This is not what's happening. In quantum mechanics, you don't have a particle going around another particle, okay? But for the sake of simplicity and to be able to communicate, we'll take this simple picture and see what will come out of it, okay? It's exactly like in the classical form here. So you have current, okay? And you can estimate the magnetic moment. It's the current times the area. And the current is the charge divided by time, just by definition. So it's the electron charge divided by the time of one period. And the area is PR squared, all right? And we can connect this with the angular momentum, which is the mass times the velocity, the linear velocity times the radius, okay? And then you can run some math here and connect these two, and connect the angular momentum with the magnetic moment. Okay, it's a simple formula. You don't have to do many difficult math. It's like E over 2m times the angular momentum. And why I'm saying all this? So I'm coming to the quantum part now. I will move on to the most simple model we have about the atoms, the Bohr model, where the atoms, it's like a planetary model, where the electrons are moving around the nucleus, okay? So we're entering the first steps of quantum physics. The energy is quantized of each electron, and also the angular momentum. And Bohr, at that time, said that this angular momentum should be just packets of a constant, this h over 2 pi, or h bar. This h over 2 pi is called h bar. Okay? All right, in modern quantum mechanics, it's slightly more complicated than this. Okay? It's still this L plus 1 h bar, so it's proportional, okay? And this L, which is the quantum angular number, takes values of 0, 1, 2, 3, 4, okay? So the value of the angular momentum is not, it's quantized. And these are the values it takes. Also the projection, this Lz is the projection, sorry, well, this is the projection along some axis. This is a model, it's a vector model, just to realize this algebraic formulas, okay? So you can have the angular momentum vector, and it's projected in different axes. For example, if this value is 2, you'll have a projection from -2, -1, 0, 1, 2. So in overall, 2L plus 1 projections. Okay? Okay, this is nice theory. Maybe we understand and maybe not, but what about the experiment? Physics is about data, is about experiment. Whatever you say, if you don't measure it, it's not there. Simply you're wrong. Simply you're wrong. You must find something else. So people back in the early 20th century, 1920, 21, 22, they were trying to see this quantization. Actually, they didn't have this clear picture at the time, but they were trying to see some quantization. So two scientists, Stern and Gerlach, they came up with this very, very historic experiment. Some experiments in physics, they are so historic, it's like the Michelson, for example, experiment, Stern, Gerlach, and some others. So what they did, they formed an array of silver atoms. So you have an oven, okay? You bake it, and you take two apertures, and you make a line of silver atoms. And you go through a magnetic field, which is not homogeneous. The field is more strong here than here. So let's see what happens in the atoms. The atoms now, you understand, they are sort of magnets, okay? You have the angular momentum, and this creates a small magnet. So if this is an atom, it's like a magnet, the north will be attracted more to the south, which is more strong, and the south less. So in overall, this magnet will follow this path. Similarly, the other, which is north-south, instead of south-north, will follow the other path, on the other way. And if it's exactly in the center, it will just move straightforwardly. All right? So how many lines you should see in this case? If we will go back here, we see two L plus 1 projections, and L takes the values of 0, 1, 2, 3, okay? So this would be a number like 1, 3, 5, 7, never 2, 4, 6. Should be an odd number and not even. Okay. Well, it was even. It was 2. Actually, this one is a postcard that Stern and Gerlach sent to Bohr and tell me, you know what, your theory is correct. This was a Christmas postcard that sent to him. But we have this problem. 2L plus 1, this odd number, is 2, which means that L, just by doing this simple math, is 1/2. But theory does not predict 1/2. So what's going on here? Well, usually, when you have such questions, the big professors, they don't provide the answers. Yeah, because they have a status, and maybe they fear that, maybe if they say something wrong, they will lose the status. But if you are a student, a master student, you have nothing to lose. Yeah. When Bohr came to this model, he was very young, he had nothing to lose. Actually, he was fired by Rutherford in his laboratory because he couldn't do experiments. Yeah, this is true. So two students, Goodsmith and Uhlenbeck, they said, you know what? We need to bring into the play some more momentum, more angular momentum. And they had this idea that we have a new quantum number, S, 1/2, and this will be, according to the math of the angular momentum, should be the same for this new quantum number. Let's say you have L times L plus 1 should be S plus 1. And the projection will be ML should be MS. Only, in this case, this quantum number is only 1/2. You can have 1/2, 3/2, 5/2. It's only 1/2, okay? So that's why you get the numbers square root of 3/2 and plus minus 1/2. Now, since it's an angular momentum, we have also the same vector model. So you have two projections, up or down, okay? And the idea was that the spin is what we call the proper angular momentum. It's the spin when you spin around yourself, okay? The electron is moving around the atom, but at the same time, it spins around itself, pretty much as the Earth. Earth is moving around the sun, but also around itself, okay? Okay, is this correct? I mean, this is an interpretation. This quantum number did the job, but it's something, it's like putting it by hand. You put it by hand and you do the job. But do you understand the physics? That's the question. And the first thing you can do is check it with some very easy exercises. For example, let's say that the electron is round and has a classical radius r and a charge E. Then you can estimate the electrostatic energy and the rest energy by his mass. This E equals mc squared. And these two should be equal because it's the same energy. Okay, let's do that. Let's equal the electrostatic energy E squared over r times kappa. Kappa is the constant depending on where you measure it, and equals mc squared. And solve for radius. Then just put the numbers, try not to do any mistakes, especially on powers. And then you will get the answer 2.8 10 to the minus 15 meter or 2.8 femtometer. It's pretty small. It's like a nucleus, okay, the size of a nucleus or less. All right. Then let's say the electron is rotating around the z-axis, okay? We can estimate the proper angular momentum just multiplying the moment of inertia and the angular velocity. It's pretty simple, okay? These two numbers. Okay, the moment of inertia is this 2/5 me r squared. Take it by some tables. I mean, you don't have to estimate this, okay? Take it from some tables. This is omega. And of course, this is 1/2 times h bar. And if you run the math and get the linear velocity, then the number you will end is 5 times 10 to the 10 meter per second, which if we compare to the velocity of light, the speed of light, 3 times 10 to the 8, this is 100 times faster than the speed of light. Will we accept this? Yeah, the linear velocity is 100 times, at least 100 times, faster than the speed of light. I mean, it's difficult to accept this, very, very difficult. So actually, this comes the question, then what is spin? Even the word spin means, to spin around, okay? So what is spin? It's not something that rotates around itself. I'm waiting for an answer now. Nobody knows. Good. Me neither. Me neither. I mean, as a physicist, I've learned that I see the facts. And sometimes things we don't understand because they don't exist in everyday life. And quantum mechanics is not in our everyday life. It's strange, it's very strange. We're not used to it. We only try to learn about the behavior of particles in the nanoscale or attoscale. All right? So it is not the proper rotation. And another strange thing is that you cannot make it rotate faster or slow it down. I mean, we could think some sort of device where we put an electron and slow down its proper rotation. No, you can't do that. There's no way. The nature doesn't allow it. Or you can make it spin faster. No, no way. You can't do that. Do you know any classical object where I can't do that? No. So this is my answer. Spin is an intrinsic form of angular momentum. It's an internal angular momentum. We don't see it as a classical angular momentum. It's there. I know you don't like this answer. I don't like this answer too, okay? But please somebody try to explain what is mass or charge. Let's try and explain these things that we have in everyday life. Mass. What is a mass? It's so fundamental that it's difficult to define it. Okay, and believe me, if you try to explain it, you'll get into many, many problems. All right, so spin is like mass, is like the electric charge. And other quantum numbers that we see in particles. Isospin, baryonic number, leptonic number, all these in this category, they are properties of matter. So once we accept this, we can continue to this lecture. I see sad faces, yeah, okay. But my job here is to tell you what is not spin, what spin is not, okay? It's not anything classical, it doesn't rotate around itself, you cannot make it rotate faster or slower. So it's purely quantum mechanical. We don't have it in everyday life, okay? All right, so let's move on now. There's something I would like to mention here. It's quite important. If you take the electron that spins around the atom, okay, it has a magnetic moment. If you take the electron spinning around itself, it's another magnet, another magnetic moment. The difference is that for the electron, there's this factor G here, okay? And this factor is the factor we have measured with most accuracy in physics, both in theory and in experiment. And in the quantum electrodynamics, I mean the most difficult part of quantum mechanics, this is the number they check to see if the theory is correct. And we know this number with 15 digits up to now. Maybe the number I'm giving is also obsolete, and this year we have another digit there. Okay? So I just want to mention how important in spin in checking the quantum electrodynamics, the theory. So let's go now, let's move to some sort of applications or situations where we find spin. Okay, I'm showing here the atom, the helium atom. The nucleus has 2 protons and 2 neutrons, and 2 electrons, all right? These are the 2 electrons. So I exchange them. So what happened to the atom? Nothing. Nothing. Okay? I mean, if somebody believes different, please let me know. Nothing. If you change the 2 electrons, nothing will happen. It will be the same identical atom. Are you familiar with the notation of wave function in the audience? Have you heard about wave function? Okay, if you haven't, it's a function, basically, that describes where the particles are. Okay? So just noting that psi, whatever, R1 or R2 is the wave function that describes where each electron is. That's all. Okay? It's a complex wave function, but it doesn't matter. It's a function. Now, if I exchange these 2 particles, well, the wave function will be the same. It doesn't change because the atom doesn't change, okay? All right, so we have this equality. From this equality, if you solve it, simply you get a plus and a minus, okay? Either it will be psi equals psi or psi equals minus psi. Simple math, simple math. Okay. Now, the upper state, it's called symmetric, and the down state called asymmetric. Is this so important? Yes. This is the cornerstone of the quantum mechanics. Because the symmetric, the particles that are described by symmetric wave functions are called bosons. And they have integer spin. Okay. I cannot prove this right now, but that's the way it is. I mean, I would need like 2 lectures to prove that this is correct, okay? This is the way it is. So if a particle has integer spin, then it is described by a statistics which is called Bose-Einstein, to be exact. And they're called bosons. If they have an antisymmetric wave function, which means a spin which is half integer, 1/2, 3/2, 5/2, etc., then these particles are called fermions, and the electrons that we'll be talking about are fermions. Okay, so let's keep this in mind. These are fermions. And for fermions, we have the Pauli, when we try to put the electrons in an atom, okay? You try to put the electrons to stay in an atom, then you can't just do it any way you want. Pauli doesn't allow it. It says 2 identical fermions. Identical means 2 electrons, okay? If they're not identical, it's an electron and a moon, it doesn't matter. They have to be identical. Fermions, electrons, cannot occupy the same quantum state, the same psi, or if you like it, the same orbital number there, somehow, okay? Simultaneously within the system. They cannot. You're not allowed to do this. So let's make a small exercise here. I have the atoms with atomic number up to 10. Okay, hydrogen is 1 electron, doesn't matter. So helium, we have 2 electrons. Let's go to lithium, okay? I will be filling now the orbitals with the spin up and down, okay? And next to it, you see how we write it. 1s squared, 2s. That's how we read it, okay? Which means 2 electrons up and down will spin up and down in 1s, and 1 in 2s. It doesn't matter if it's up and down because it's alone. Now the next one should go to the 2s. It has to be down. And when I say down, I mean the projection of the spin, okay? Spin is 1/2. The projection should be down. Okay, here it is. In boron, it's easy. I'm going to add another electron. So my question is now, what about carbon? Where should I put the electron? And with, I had the first, sorry, but the guy up there was spared to answer. I can't hear you. In the fourth. Correct. You want to tell us why? Okay, it's always a matter of energy. Okay, it's always a matter of energy. It goes there. I need a full lecture to explain why it goes there. But anyway, it's called something called the Hund's rule. It's not any rule that Hund just made up. It's something that comes out from the calculations. But in order to remember it, we give it a name. It's Hund's rule. So spin should go up. Simply because if it goes to the first orbital like this, it will have higher energy. So nature goes to the lowest energy and then fills up the levels. Okay, then I can move to nitrogen, and then we'll start coupling the electrons, like this and like this, up to neon, where we have a full 10 electrons in the atom. All right? And all this due to the spin. All this to this small magnet that exists inside the electron, and we have no idea how it's there. It's just there. So the first application is the periodic system of elements. I mean, the spins tell the electrons where, to which energy level to stay, and of course this energy level, these states, define the chemical properties. Because the chemical properties is all about the outside electrons, the electrons in the outside the atom. They are making the bonds there, okay? So the spin defines the levels, basically, of the atoms, and this defines the chemistry, and therefore, the periodic system. Can you imagine chemistry without spin? Now, this is a real question. Can you imagine if, let's say, you're God and you create a new world with no spin? Would there be chemistry with that? There will be some sort. There will be some sort of chemistry, but not that. Not that rich chemistry. I hope I convinced you about this. So, yeah, so I come now to another application sort of spin. Most materials, the electrons exist in pairs. So if you have pair, the spin is 0. It's 1/2 minus 1/2, roughly, very, very roughly, so this gives you a 0. However, in some elements, you might have unpaired electrons, like in carbon, like in, these, as I showed you earlier. These are expected to have a net magnetic moment, meaning they can be magnets somehow. Okay? Depends on the element, but these are the candidates for magnets. And let me show you here just a picture of what magnet means. Let's say you have a material called diamagnetic. Diamagnetic is us, okay? The flesh and bones. So if we put ourselves in a magnetic field, a strong magnetic field, then another field will be induced, this yellow field will be induced in the opposite way. Why? Because this magnetic field imposes, makes our molecules look like magnets simply because they pull them somehow apart. And of course, this field cannot be in the same axis as the field you impose, because simply you will create field out of nothing, out of 0. Okay, so they go the opposite way. It's called the Lenz's law. You try to make it more, it goes back, simply to keep the balance. But in paramagnetic materials, these small magnets exist there. Exactly, very small, and they are, all around in different directions, so the field is 0. But if you put a field, then they are aligned. So the small magnets are aligned, but it's not a strong alignment. It's not a strong field. That's why it's called paramagnetic. Now, and in these two cases, it's not only about the spin, it's also about the angular momentum. Okay? But if you go to the ferromagnetic materials, then the spin comes there. You have states with many spins that are aligned and make whole areas. When I say areas, I'm talking about macroscopic areas, millimeter size in the material. And if they are aligned, then they make magnets. The magnets we have in nature. All right? If they're not aligned and you try to put some field there, then they are all aligned and they give you the electromagnets. You force a field and they give you the electromagnets. Now, we have also some other cases, ferromagnetic. I won't go to this, it's much more detailed. We just have to keep in mind that the spins in some material, they can be aligned. And this is the reason that we have magnets, the permanent magnets. And even if these areas are not all well aligned, just with a small field, we can make a magnet out of them. So the question is, can you imagine life without magnets? Everyday life, without having them. If you don't have the spin, you won't have the magnet. Can you imagine how our life would be without the magnets? We would be still alive, but with no magnets. Okay, so I'm going back to the Pauli exclusion principle and say that, okay, this is okay for fermions. What about bosons? Two identical bosons can occupy the same quantum state simultaneously within a system. The spin is integer now, so they can all go to one state. There's no rules, there's no spin up or down, they can all go to the same state. Actually, this idea was proposed by Einstein. If you cool, because if you want to put something in the lowest level, okay, you have to cool it. It doesn't mean because they're bosons, they will go to the lowest level. Because if you have energy, it's like having money. If you have money, you spend them. You don't stay home. Believe me. If you have money, you spend them. Okay? Nature, if it has energy, it spends it out. So if you take the money, the energy out of the system, then it will go to the lower level, which is your room at home, alone. That's the lowest level. Okay? You have money, you go out. That's the idea. So Einstein proposed that we'll have a new form of matter if we achieve this, to put the particles all in one state. And you will see why. I have a video here. I hope it will play. Come on. Sorry. Anyway, this is some atoms, and you see the energy diagram. So the atoms initially they are in different energy levels, up, down, and then we cool it. We start cooling it. When I say cooling it, close to zero, minus 233, 73 Kelvin. Okay? So you see now the atoms, they spread their wave function all around. They go lower and lower in energy. This is a Bose-Einstein condensate. This is one wave function. All the atoms, they came together and they blend in one state. This is one state. It's not 10 states of 10 atoms being together. This is one state. That's why they call it a new form of matter. And this was proposed by Bose and Einstein back in the early 20th century. And that was done in the late 90s. They achieved it. Yeah? And it's a very nice story about how they managed to achieve it. Do I have, Kostas, 2 minutes to say the story? Okay. One of the guys that received the Nobel Prize, Ketterle, told us this story at the time, back then. And it goes like this. In order to see this Bose-Einstein condensate, in the experiment, you see some dot. If this dot becomes elliptical, then it's what you see here. So they set up the experiment, and for days or months, they saw nothing. They were so frustrated. Then one night, Ketterle went home. Around 1 or 2 o'clock, in the morning, they saw it. They called him, come here. I was in New York. He goes next day, early in the morning, 5, 6 o'clock. It wasn't there. They spent all day. He was so tired, he went home. Around 2 o'clock, it was there again. This happened 2 or 3 times, so he decided to stay during the night. And again, the third night, it was there. So what happened? The metro stopped at 2 o'clock, so there was no noise, and they saw it. At 5 o'clock, the metro started, so there was noise. They missed it. So they made the proper arrangements, and they finally saw it and measured it and got the Nobel Prize and everything. Okay. So it was the metro. It was the metro. Okay, so let's move to another issue. That's a bit more difficult issue. Okay, let's try and put some math in this lecture. I will bring to your attendance what we call a two-level atom. Of course, you know that atom has infinite levels. But when I say 2 levels, I mean the 2 levels that will do the job. I will have 1 electron in level B, and I will come with a photon and excite it to level A. So only these 2 levels come into play. The others are just spectators. So I can forget them and call this 2-level atom. Right? Now, when you try to describe this atom in quantum mechanics, you don't know where the electron is. If it's in A state or B state. You have no idea. So you have no idea. So you have to take this into account. Okay? It's A plus B with some weights. Come on. Anyway, with some weights. Sorry about this. This is we call it superposition principle. You don't know where it is. You just add them with some weights, and then you will find it in the future. Of course, here I have to take into account the time, because each wave function here, as you here, it has this term. This term, for those who don't know about this complex number, it's just a sinus or a cosinus, something that oscillates. That's all. Now, you have to take this wave function, put it in the Schrödinger equation, okay, and put also the electric field, which is like a laser or something, and solve it. This we will not do here. This you will do in the university, in the physics department that I wish you go in a few years, and only if you take my class. So you're safe for now. Okay, the result is this. The result is this. We have something called population inversion. It means that initially you start with atoms that they're all in the ground level. And you take electrons and put them in the upper level. All right? So this difference, upper to lower, it's called population inversion. This is the principle for making a laser work. You need to take the atoms, the electrons, to go to a higher level, and then continue from there on to have a laser system. Okay? The same principle. Now, if you estimate this, simply it's just a cosine of this quantity. This is called Rabi frequency. It's a frequency. It depends on the strength of the field, divided by the h bar. And this strange letter here is simply quantum. It's a calculation. It's a matrix element. I mean, you calculate how probable is to go from here to there. That's all. It's a number. Okay. So basically, it's proportional to the outside electric field that you put. All right. So the more strong the field, the more faster they oscillate. All right. So why I'm telling you all this? Now, for example, I'll give you the plot of a cosine, but that's all I'm giving, okay? It's very simple. So why I'm saying all this? Do you know any system that has two levels? Spin. Spin has exactly two levels. Projection up, projection down. All right? So we can use all this theory to our benefit. To our benefit. Let me show you how. We have something called nuclear magnetic resonance. Nuclear. We don't like this term, but let's see what it is. Basically, not only the electrons, but in the nucleus, the protons and the neutrons, they have spin, 1/2. They have spin 1/2, okay? And actually, the nucleus defines what is the element. The atomic number, which is the number of protons, defines what is the element you're looking for, okay? It's chemistry. Let me tell you that nuclei have many protons, but they come in, the spins, they come in pairs. You have 11, for example, protons, you have spin 1/2, because all the other 10, they have coupled, okay? This is a general rule, it's not, of course, the full picture. But anyway, what I'm trying to say is that the atom has spin. Okay? So this spin will react with an external magnetic field. All right? So in order to have these two states, we're going to prepare the nucleus. What do I mean prepare? If you have an electron or some spin, this only interacts with the magnets, with magnetic fields, not with electric fields. All right? So unless you put some magnetic field there, the energy of these levels will be the same. Okay? Because there's nothing to split these two levels up and down. If you don't put a magnetic field, they will not split. So what we do, we put a very strong magnetic field. And then you have something which is random around to have an up or a down, a low energy or high energy. Okay? So you split the two levels like this. All right? And then what do? You come with a photon. Only in this case, it has to be a very, very low energy photon, radio frequency. And you drive the population from the upper to the lower to the upper level back and forth. Okay? And you measure this photon that comes out. And if you measure it, you know what is the element, because these two energy levels tells you exactly what is the element. And what do? You do what we call, the physicists call it nuclear magnetic resonance, but if you try to say to lay people nuclear, you lost them. Nuclear means nuclear bomb. I mean, they're going to bomb me, they're going to kill me there. So, of course, physicists were smart people. Okay? We'll change the name. We'll say it magnetic resonance imaging, MRI. It's exactly the same. MRI sells, NMR doesn't sell. It's so simple. Okay? It's so simple. Have you ever been to an MRI scanner yourselves? Yeah? Yeah. It's frightening. I mean, I teach this stuff more than 10 years now, but last year I had to be in one of them. I made, my first was like, okay, there should be a clock here, counting the time, because I lost track of time. It was like being there for a year. Yeah. Anyway. So, I will come to the last part of the talk, and this is really the most difficult. After the end of the talk, of course, we can discuss about spin most things. So that's why I keep it short in time. and this comes to the modern quantum mechanics. It's the Einstein-Podolsky-Rosen paradox. I will not talk exactly about this, but a version of this that Bohm brings into play that has to do with spins. So it's the EPR, Einstein-Podolsky-Rosen, Bohm. It's a thought experiment back in the 30s, 1930s, where people didn't have the luxury to do delicate experiments to prove it. But we had the luxury to have great minds at the time and propose what experiment we should do to find it. Okay? So the experiment is simple, the thought experiment. Gedanken experiment. Sorry about this. Okay? Is this. You have a source in the middle. Actually, I have a source. You have a source in the middle. And this source emits 2 electrons. Actually, it's an electron and a positron, but you have 2 electrons. Electron and positron because you have a pair production, which gives you electron and positron, so it's more realistic. But we can think of 2 electrons like this, okay? They go opposite directions. And the state of these electrons is prepared, so these are like this, one up, one down, okay? Because you can have also this. But let's forget, let's make it more simple. It's a thought experiment. It's a thought experiment. I can set whatever I want there. So it's like this. And in one side, you have Alice with a detector, and the other side, you have Bob with another detector. All right? This state is called singlet, for reasons that you don't need to know now. All right? So the first state is, let's say, along the axis Z is up and down, but at the same time could be like this. This is also singlet. So which one is it? Well, you don't know. You take both of them. Huh? You will take, quantum mechanically, both of them. It's this and this, okay? This state is called nowadays entangled. Entangled. Because the particles, they somehow talk to each other. I mean, if the spin is like this particle cannot change the spin without the other changing it. It's in the same state. All right? So these are entangled. Now, let's take now Bob and Alice and take them far apart. Very far away apart. I mean, not Thessaloniki. Let's take them to the moon or outside the solar system or at the end of a galaxy. You take the detector of Bob at one end of the galaxy and at the other is Alice. It's about 100,000 light years, okay? And Bob decides to measure now what is the projection of the spin. And he finds it up. What will Alice find? Down. Why? Sorry? Yes, thank you. But I'm talking about the physics of this, the moment you make this thought. This is a thought experiment by Einstein saying, you know what, guys, this can be correct. Because if I take this so far apart, okay, and I make this measurement, then you're telling me that simultaneously the other electron will have the spin down. But how the information travel all this distance simultaneously? That was the question there at the time. That was the question. So Einstein was saying, you know, all this is wrong because simply it doesn't go with my theory of relativity. You need to go with the speed of light from one place to the other to travel to information. It's not a phase, it's information, okay? So the experiment, right here, yeah. So the experiment was done like 60 years later by Aspect in France, and Einstein was wrong. Einstein was wrong. Of course, the experiment took place in a place like this. You don't have to go to the edge of the universe to do this measurement. But whenever you measure the spin up, okay, the experiment is a bit more complicated than this simple picture. Okay, that's why I'm not going to tell you. It has more states there, and it's a bit more complicated. But this is the principle. All right. So the answer to this. Before I go to the answer, people try to explain, make attempts to explain this, all right? So they start talking about hidden variables, saying that, you know what, quantum mechanics is not exactly well-formed. There are some sort of variables hidden somewhere there that if you find them, then this problem will be explained. And in the 60s, I think Bell came up with some inequalities, okay, that if they are obeyed, then you have hidden variables. If they violated, then you don't have hidden variables. And the ASPE experiment proved that there are no. The Bell's inequalities are violated, there are no hidden variables, that's the way nature is. And the answer is that there's no transfer of information. The information is here. No matter how far you take it apart, you did not transfer any information. It's all there. It's in the wave function. In the wave function, you don't travel information from one place to the other. It's all there. It's just quantum mechanics. That's the way it's working. That's the way it is. And the proof of it is that today we use this entanglement in quantum computing. We have entangled spins to do very, very fast calculations that we could never think with a normal computer. Or quantum cryptography. This is something I like so much, the quantum cryptography. I mean, in the past, you did cryptography with prime numbers. You split them in half, you send the one prime number there, and then you have the other, and then they match, and you say it's good. Now, let's say you travel information. If I try to steal some part of it, it's a measurement. It is a measurement, okay? The other part will have, you know, the spin up or down, so I know that somebody is trying to cheat me, and I stop it. There's no way to get something from the wave function, to steal it, without the wave function going to one of its values. And the last part is the quantum teleportation. Now, please, we're not talking about beams, no, we don't teleport mass, okay? You can't take you and put you in another place. This is something people don't understand. It's information that you can teleport. Simply by this simple, not simple, but anyway, this rule, okay? So this is pretty much what I sum up to tell you today. And yeah, it was an overprime 22. So thank you, and I hope that we'll have some questions and have some discussions about spin. Thank you. I try to keep it, you know, let me say, in your level somehow, without too much mathematics. Otherwise, we would get lost, and we take the discussion to other levels. I mean, people who really know the mathematics of quantum mechanics can discuss this in a much, much different level, okay? But as a physicist, I think that the people, even those who are not physicists, should be able to understand basic stuff and not talk about flat Earth, aliens, you know, stuff that it's pointless even to get into one discussion. All right? So.
Thank you very much, Professor. Please.
Ask anything you like.
We have a few time for a couple of questions. There. Περίμενε λίγο να έρθει το μικρόφωνο.
So spin could be energy trapped in a particle that makes it spin very fast, faster than the speed of light.
You're asking if the spin is energy that is trapped in a particle and makes it spin?
That makes it spin, yes, spin around.
No, it's not. I mean, it's a sort of angular momentum that is a property of the matter. It doesn't spin. It doesn't spin in the classical way, like this. No. It has an intrinsic and internal angular momentum. I don't know how. But let me give you an example of the normal angular momentum. Okay? That has a quantum number 1, 2, 3. Okay, 1, but there's also 0. L equals 0. 0 means no rotation. At least that's how I understand it. What does 0 means for the angular momentum? I'll give you an example. If you have an 8, if it goes like this, okay, in this way, because it's a vector, goes like this, and the other goes like this. So the sum is 0, but it's not that. the S orbital is spherical. Okay. So my question is, where is the 0? You see, in quantum mechanics, it's very easy to fall in traps. Because we always try to interpret it based on our classical world. It's not. It's not. And always I think the best way to discuss about this is to give examples of things that you think you know so well.
Okay, thank you.
Okay.
I didn't understand the asymmetry that leads to particles with different spins to react differently to the same magnetic field.
Let's see. Help me here, which one you mean? This? Oh, sorry. Is that you're asking? Symmetric and asymmetric wave functions? No. Κώστα, έχει μικρόφωνο. In the experiment, sorry, Stern-Gerlach experiment. Yeah. Well, let's see. Here, I simulate an atom with a magnet to make it more. Okay. So this magnet is an atom. All right. Now, the magnetic field here is non-homogeneous. You see here, this has this geometry. So basically, the field goes like this. You have more lines in the upper part than the lower part. Okay, and the derivative of this field, the rate of change of this field is the force. Okay, so this part receives higher force than the lower part. So overall, the force is going up. It moves it up. That's why it will finally go in some up place. Inversely, if you have an atom that has south, reversed its magnetic, its magnet, the way the magnet is in the area, then it will have more force on the upper part again, but to the lower now, and less on the upper. You can tell this by these two vectors. This will drive it down, and will go down. Now, how down is that? Please see this number here. 1 millimeter. That's 1 millimeter. And actually, the experiment was done by students, of course, and they have to put their eye in this screen for hours. For hours. And some of them develop cancer. That's true. Yeah. Actually, they have another story. They say that they were able to see this because at the time, Europe was quite poor, and they used to smoke cigarettes with were not the best cigarettes in the market. Okay, and the smoke of it was lying on the screen and make it easier to observe them. But they have to look for hours there. Look for hours in 1 millimeter. A very difficult experiment. Well, of course, nowadays you can find it in any laboratory in departments, but that's the way it is. The magnet receives more force on the part of the other, or the other. Goes like this. Of course, if you put, I gave this example with 2 projections. If you put 5 projections, you should be able to see 5 traces. This is just an example to understand the picture. Now, if I had a homogeneous field, nothing would happen, because the force on the upper part should be the same as the force on the lower part. So, I give these questions to my students, what would have happened, how many traces I would see if the field was homogeneous, and everybody has a wrong answer. They say 0. Oh, 1. We'll just go through. But anyway, I'm not so... Yeah, I think he wants to continue discussion. Costa.
But then, if it has to do with the spatial orientation
Yes.
of the atom,
Yes.
then why is it like 1/2 or -1/2? I mean, if it can be like every orientation.
Yeah. If this was a classical atom, without spin, okay, then you would expect to see some distribution, some even distribution. Yeah. That's why this experiment was done. They want to see, will be an even distribution, or we expect something. I mean, at the time, in 1921, there's no Schrödinger equation. That comes in 1926. We have only the Bohr model. But also the Bohr model expected some condensation of the angular momentum. They have no idea about spin, okay? So it's an experiment somehow blindfolded. I understand your point that if I put some atoms there and they're not quantized in the angular momentum or the spin momentum, then you should see like a normal distribution. So there's no quantum field, there's nothing. But they saw two. They should see, they were expecting more, like an odd number, but they saw even. And that was the problem. For many years, because you see, Goodspeed and Nullenbeck, they took us 4 or 5 years to say that we introduce a new angular momentum called spin and blah, blah, blah.
Okay, thank you.
Yeah. I mean, it's very constructive to understand that these people in the early 20s, they were brilliant. They were brilliant. I mean, they found the physics that we will be using for the next 1,000 years or more. Sometimes I say to myself, if I were born at that time, I would have a Nobel Prize.
You're still young.
Whatever you do was diamonds.
You are still young, Professor. Thank you very much for your very active presentation. Sorry. Please.
Even though I'm not sure if you mentioned it, does the spin of electrons affect the atom as a whole or not?
If the spin affects the atom as a whole?
Yes.
Definitely, yes. I'll give you one example. Very, very simple example. Spin is a magnet. I hope I convinced you that spin is a magnet, okay? I should go this way here. Oh. Spin is a magnet. Also, the angular momentum is a magnet. So you have two magnets at the same place. Don't you expect them to interact?
Of course.
Of course you do. The nucleus, yeah, it's called spin orbit interaction. That's what it's called. This thing will change the energies of the electrons that basically come from the Coulomb interaction. Okay, they will change the energies in the third, fourth digit. Okay, they will split the energies. This is what I did in the Rabi oscillations, where I put the strong field is to split these energies. You split them by a small amount of energy, but still you split them. Now, this is called the fine structure, and also they interact with the spin of the nucleus. Actually, the spin of the nucleus interacts with the spin of the electron and the angular momentum of the electron. That's called hyperfine interaction. It goes to the 6th or 7th digit correction. Of course, it's there, yes. Not to mention that in some cases, spins plays the most important role in decays, things that decay. For example, I take the helium atom, okay? You have electron up and down. I take this electron and take it to the 2p state. In 1.6 nanoseconds, it will go down. 1.6 nanoseconds. I take the spin now and put it like this. There's no way this will go here. There's no way. This state lives about 1 second. About 1 second, 1/7 of a second, which means that it's like you living 100 billion years, 9 orders of magnitude, let's say. 9 orders of magnitude. It will finally go down for reasons that I don't want to mention now, but that's the way it is. Simply, the Pauli rule tells you you cannot go there. And this is a spin. But if it goes like this, it will go in 1.6 nanoseconds. So yes, it does, very much.
Thank you.
Okay, I think now it's over. Thank you very much, Professor. You saw what happened.
Thank you too.
And what you caused to the students. Thank you very much.
I must say, I'm very glad to see young people be interested in physics at this age. I'm so happy about it.
You mentioned something about chemistry. Spin belongs to physics, chemistry, both.
well, I can say a joke about chemistry here. It's okay. Chemistry is the physics of the electrons in the upper level. That's what it is.
Great answer. Thank you very much.
It is.
So,
Thank you.
it's my privilege to present the next and the last lecture of this session and this summer school. I'd like to invite Professor Bradislav Obradovic. Thank you very much for being here. He came from Serbia. He will be talking about the interference produced by laser light meeting of the classical and the quantum physics. Thank you very much, Professor.
Dear organizers, dear Costa, thank you for inviting me to be part of this wonderful camp and to see so many young people that are interested in physics. My talk will be about, you see the title, about the interface produced by laser light and when meeting classical and quantum physics. You can see that it's most about classical physics, but you can find that something like on the back door comes quantum physics, and that is very important for understanding what we done in experiment I will show you. So during your lectures in City Hall, I've seen that one of students presented a double slit experiment, very important experiment in physics, and he tried and he realized this experiment by himself. We also do something like this, but we are with some improvements. And Costa, do you have pointers? Okay. I will. Is this? Okay. With some improvements. We use helium neon laser. I will explain why we use this laser, and use this crystal for making two lights. From one light, when passes light to this crystal, this will obtain from one rays we can obtain two rays, and after that, from this point, it looks like double slit experiment, and we look at the screen what happens. There are some improvement experiment. We recording what is how looks laser lights, what is actually inside the laser, and for this purpose we use scanning Fabry-Perot interferometer, spectrum analyzer, oscilloscope, and also we use here polarizer. All about these parts I will explain you in this experiment, trying to involve you in experiment and try to explain in level that I propose you have to understand experiments from the beginning. This is simple experiments. You can see this is laser, it's beam splitter, lens, here is crystal, polarizer, this is screen, oscilloscope, and all these recorded using simple camera from smartphone. And I will show you the, I hope that is, okay. Just look at experiments. On the right side is what is in the laser. On the left side is what you can see on the screen. Just want to try to compare what you're looking on the screen and what you're looking on the oscilloscope. This is vibration because tram. maybe, but I can use this. Try to see the difference during the experiment. That would be enough. Okay. I try to move to the next part. And what did you see? You see that as arise one peak, we called it one peak from the laser. I explained what this means. You can see, sorry. You can see clear interference fringes. When it started to decrease, this is one peak and also second one, you can see clear interference fringes. I explained how this is obtained. But if you have that second peak arises, interference fringes start to blur. And where both peaks existed, there is no any interference. What happens and how we explain this? First, I want to tell you is the modification of double slit experiments. Double slit is traditionally makes when you use two slits very close to each other, and on the screen you can see interference fringes. But instead of this, we use crystal that has that possibility to split the laser lights in two laser ray in two rays, which we call ordinary and extraordinary. But these two rays, you can see these arrows, means that two rays have mutually orthogonal polarization. What is polarization? I will also explain later. And how looks this crystal? This is Icelandic calcite, and you can see how it works. You have one line. When you look into the crystal, you can see two lines. And that two lines have mutually orthogonal polarization. But before I continue, I need to, for interference, to see how you can how you can calculate interference fringes, how you can calculate distribution of bright and dark regions. But for this purpose, we have to connect light with some you probably heard is electromagnetic wave. And for this purpose, I will move back in that footnote, and you can see how is electric charge is connected to electromagnetic wave. Let's at the beginning, we look at the charge that is not moving, and what we have is constant electric field that depends linearly of charge. And what happens when charge start to move? When charge start to move, we will obtain magnetic field. Magnetic field surrounded this charge, and magnetic field depends on the velocity. It's linearly dependent on velocity. So the next is what happens if we change velocity of this charge. If we change velocity of this charge, it means that we introduce some acceleration, and what happens that magnetic fields will change, and that will induce electric field. This is a known picture from, probably you learned about Faraday law of electromagnetic induction. For this purpose, you can see here a permanent magnet, and there's a line of forces of magnetic field. If permanent magnet do not move, magnetic field doesn't change, so you cannot register here any current that will be passed through this conductor. But if you start to move this permanent magnet, you can see that is current passing through this conductor, and this is current is consequence of changing of magnetic field. But you know that current is directional moving of charges, and what forces charges to move. What is forces charges to move is electric field. So you can say the simple experiment that changing of a magnetic field induced creation of an electric field. And this is looking something like this. If you change magnetic field, that electric field arises. But what I must tell you here, that this electric field has no origin in charges like this electric field. This is electrostatic electric field. This electric field we can call dynamic electric field. And this electric field has properties very similar to magnetic field. And this is what Faraday measured and what Maxwell organized in his famous equations. But what Maxwell do more is what was the situation if we use we change acceleration. So if we change acceleration, that will that will cause the change of electric field, and cause a change of electric field will induce a rising of magnetic field. So you can see here that where charges have motion that is changed in velocity and acceleration, you can produce electric field, and after that you can produce magnetic field, and this is the way how electric and magnetic field is mutually coupled. And what do you think? What kind of movement will produce electric and magnetic field, and after that you can see that it's produced electromagnetic waves. So you can see here is some kind of periodic motions, because during periodic motions one charge can produce together magnetic and electric field, and that fields are connected like in chains. So one of method to produce this electric and magnetic field is to put one conductor and change voltage, like in not DC current, but current that is changes. So if you change current, that means that you change position of the charges in this rod. But when you change position of the charges of this rod, you change electric field. So for different position charges of the rod, which is forced by changeable current, you can change the electric field that is produced in the charge, and also do not forget, there is also arises magnetic field. And because these charges is moving with changeable velocity and beside the electric field produce magnetic field, and magnetic field also produce electric field. And that mutual connection between electric and magnetic field forms some kind of waves, which is called electromagnetic waves. And they are mutually connected. They produce each other's. And we can see one of exemplar how is electric field and magnetic field connected, and they're at the right angle in what is called electromagnetic waves. And that electromagnetic waves, before I start with this, you can we are all surrounded with electromagnetic waves. I do not talk about light at the moment. I also only about electromagnetic wave that is produced by moving of charged particle. And that electromagnetic wave you have in when you communicate with your mobile phones, for example. There are in mobile phones some charge, there are changes, they are moving oscillatory and produce electric field. But there are also charges that move, for example, in device which is called magnetron and produce electromagnetic field, which is used in microwaves. So why I put these microwaves here? Because you know that if you put some soup in the microwaves, you can heat the soup, but how it happens? It happens because electromagnetic waves carries energy with them. Carrying energy means that energy is using from somewhere. And this energy is from electrons. They are moving oscillatory in some devices. But what is the speed of these electromagnetic waves? Speed of electromagnetic wave you can calculate it relatively simple in, for example, in using your microwaves, microwave oven. There is one example. What is the length? This is half of wavelength of electromagnetic wave microwave oven, and probably all microwave ovens have on the door, on the backside, what is the frequency of electromagnetic wave that is used. And for example, I can suggest you one sweet experiment. If you use chocolate and melted chocolate in some plate and put this plate after the chocolate made, after you make some plate with chocolate, but it's not boiled, it's cold, and put in microwave oven, you can see at the position where is a maximum of this electromagnetic wave, the chocolate start to melt. And this position start to melt, for example, at this position, you can measure half of wavelength. And when you measure half of wavelength, and you know frequency, you can calculate what is the speed of electromagnetic wave. So this is the one method that you can measure speed of electromagnetic wave, but back to serious physics, and you can see serious with physics with covered with more mathematics. You can see these two equations. These two equations is a consequence of famous Maxwell equations. There are 4 equations, and I just move a little back to show that in this situation, I actually intuitively show you these 4 Maxwell equations. This is first equation that show you that origin of electric field is charge. That origin of magnetic field is charge that moves. Second equation. This is third equation that say that electric fields can be produced by changing of magnetic fields. And part of fourth equation that say the magnetic fields are also produced by changing of electric field. So this is the intuitively presented Maxwell equations. But if you presented this mathematically correct and solve these equations, you will obtain these 2 equations which connect electric field and changes of electric field by distances. This is x, y, z coordinates, and how it depends of changing of electric field by time. And also symmetrical, how it changes magnetic field by distances, how it changes by time. And if you try to make simple dimensional analysis, you can see that on the left side you have meter on square. On the right side you have second on square. So when you connect square meter and square seconds, this is probably square. This part is probably something that is connected to square of velocity, and is actually is. This is velocity of electromagnetic waves, and you can calculate velocity of electromagnetic waves only if you know the electric constant and magnetic constant. And what do you think? What Maxwell observed? What calculated? What is the value of this velocity? First, before that, you can see that this is called sorry. This is called wave equations, and these wave equations connect some of parameters, some of this is electric field, how is changing by time, by space, and you can see that one of realization of this change of electric field is this wave, and lambda is period in space, and also t is period in time. So in that equation, that solution of the equation, coordinates, space is connected to time, and they are coupled in this part. They are connected, space and time, and also this sinus function. That means that it changes together in space and time. And we move back to this velocity, and how velocity. What is the velocity of this this wave, of this electromagnetic wave? And Maxwell calculated and obtained in 1965 that this velocity is like this. But you can see that what is claimed, that this velocity is so nearly of that of light, that it seems we have strong reason to conclude that light itself, including radiant heat and another radiation, if any, is electromagnetic disturbance in form of waves propagated through electromagnetic field according to electromagnetic laws. So he claimed, according to this velocity, this velocity he calculated, this velocity was measured by other researchers, so he claimed that this light is electromagnetic wave. There is also one reason why he claims so, because electromagnetic wave is transversal wave. That means that oscillation of electric field in that direction, and waves propagate in direction that is orthogonal to disturbances. And also the light is like this. There's this proved in experiment, probably 50 or 60 years before Max Planck. They proved French scientist Fresnel and Arago that light is transversal wave. So according to these claims that velocity is very close to the measured values and that both waves are transversal, Maxwell concluded something like this, that light is electromagnetic wave. But you can ask, is it maybe accidentally that these waves have this very similar value for their speeds? For example, you know Usain Bolt. He can run as gazelle. Does it mean that Usain Bolt is gazelle? We do not know. But what is there exists some light that is produced by accelerating charges, and actually exists in, for example, synchrotron radiation. Synchrotron radiation means that electrons are moving along the circle in the presence of magnetic field, and they emit radiation which can be in infrared, visible, ultraviolet region. So light can be produced by accelerating charges. And also in free electron laser, you see different magnets and electrons move like that. So it's obviously we're changing velocity of acceleration and emit lights, which is also can be from infrared to ultraviolet. So there exists a system in which electrons, charged particles can move and emit light. You can see I took two examples that is noticed of synchrotron radiation in emission of active galactic nuclei, this part, or one remnant of a star. This is here is this nebula, and you can see this bluish light. This is synchrotron radiation. But what about atoms? What about light that is come from atoms? And for this purpose, I will move back in history and probably with Newton, and the most part is doing during the 19th century. But what was done by Isaac Newton? He's famous, but you know there's 3 Newton laws in mechanics, gravitation law, but it's also known by experiments he has done in optics, and he published a very good book in optics. And what the reason that I mention him here, because he used simple device like glass prism to resolve white light to different colors of light. And this effect is called dispersion, because there are different speed of light inside for different frequency. Inside this glass prism, you can observe dispersion of light, and you can observe different colors. And Newton formulated what we know as how we can see colors. For example, this my blue shirt you can see because that's light, and light in me, and all colors are absorbed except this blue light, and blue light comes to your eyes, you can see it's blue. But this is if you have some source of light, and this is in reflection. But what about the source, the emitted light, like candle, or for example, like fireworks? You've seen fireworks, and you've seen fireworks, there exist different colors. You can see, for example, yellow color. Yellow color is the mostly from atom sodium and sodium salts. You can see green color from copper, or you can see something like pink color. Pink color is for magnesium. And there are very important discipline in physics, which is called spectroscopy. Many spectroscopies during the 19th century measure different atoms, how emit different atoms. And for this purpose, they use a simple flame. In flame, they put different salts and measure what they observed. And what does this mean? If you have some continuum spectra, like for example, molten iron, you will see some continuum spectra. But if you have hot gas, like in this flame, you will measure something like emission spectral lines, line spectra. But you have cold gas, which is enlightened by continuum spectra, you can see some black lines in the spectra. So, during the 19th century, also Faraday made different experiments using these vacuum tubes and gas in vacuum tubes, and obtained different colors for different gases. That means that really atoms emitted lights. So there are many other proofs. For example, you can see how looks spectrum from hydrogen, from helium, nitrogen, oxygen, from different, well, I think this is really measured. This is synthesized. And you can see in this picture what some spectrum is very poor for only several lines, but is some very rich with many of lines. So what we conclude from spectroscopy, that atoms emit lights. And how we can explain this? I told you this because we have different model. When claim Maxwell, you know, this is 1865, that the dominant model was model of John Dalton, solid sphere model. This solid sphere model is a neutral atom. In neutral atom, you have no any charges. How light is produced according to Maxwell? If you have no charges, they move. And there was a huge problem during the 19th century, and there are some exotic solutions. For example, Lord Kelvin, you know about Kelvin scale, proposed that there exist some vortices inside something that is called ether, and that vortices oscillate and cause oscillation of the ether, and this oscillation is light. But in 1897, J.J. Thomson discovered that exists something that is smaller than atoms. That smaller part is electron. And after that, proposed this model. I think this picture is wrong because they are not particles like positive particles like this in model, but all sphere is one charge, but exist some charges, some electrons. And after scattering, I've seen that professor presented during your workshops. After the measurements of Ernst Rutherford scattering experiment, finally is formulated this planetary Rutherford nuclear model, and after that Niels Bohr planetary model. What planetary model means? It means for inner planets that instead of sun is nucleus, instead of planets is electrons. And electrons are moving periodically, which means that emit electromagnetic waves. Electromagnetic waves is light, and at first it seems it's okay. But I remind you about microwave oven. Microwave oven means use electromagnetic waves. Electromagnetic waves carries energy. And what is energy for these electromagnetic waves? They transfer kinetic energy of electrons to electromagnetic waves. And that means that electron will emit electromagnetic waves and losing its energy. After losing its energy, he is changing its position and will be collapsed in the nucleus. And this was a huge problem. And another problem? What is predicted this theory? Because this changes, electrons move continuously, that will be produced continuum spectrum. But what is obtained? Discrete emission spectrum. How to resolve this? And Bohr resolved using his famous postulates. And his famous postulates means that electron in atoms orbits the nucleus. So his planetary model is valid. But electrons cannot emit during the position at that orbits. It can only emit when it jump from one orbit to another one. And what is emit? This is what I highlighted, electromagnetic radiation. So Bohr also claimed that electromagnetic radiation, that light is electromagnetic radiation. So we can move back and see how to use this proposition that light is electromagnetic radiation in explained experiment. So you can see electromagnetic waves looks like this. You have these values like Silk Road frequency, like Thales wave number, and how is it connected to periodic time period and wavelength. And you can see that this wave is only in one plane. That means that you can use this wave plane, and you have used this projection. This kind of electromagnetic waves cause polarized electromagnetic waves, and plane where this oscillate electric field is called plane of polarization. And you can see how it's, during the time changes intensity of electric field, but no changes plane of polarization. It is the same. Let's go move to laser interference. Now we know that light is electromagnetic wave. And in double slit experiments, we have one wave from this side and one wave from this part. So we have two sources, and in that point, we have two electromagnetic waves. Two electromagnetic waves means this is the result. That means that we have at this position electric field exchanges in that way, and that position the exchange in that way. And as you know from the course of physics, electric field you can sum as simple vectors. So in that position we have electromagnetic wave of 1, 2, and what is really measured is not electric field. Really measured intensity of electric field. And intensity of lights. Intensity of lights is square of electric field. And these brackets means this is average over the time. Why is average over the time? Because electromagnetic field have frequency, that means this changes per seconds, about 10 to 15. 10 to 15 is about millions of billions time in seconds. So we cannot measure electric field. Only we can measure, this is intensity, this is square of electric field and average over the time. And what we can measure, average of square of electric field. Square is simple scalar products of two vectors. When we made scalar products of two vectors, we obtain something like this. And both intensity, we obtained intensity of first wave, intensity of second wave, and this part is neutral connection between these two waves. And when we average this is somewhat, it's not complicated. You probably are involved in the trigonometry, so I will skip this. This is how average over the periods move. And finally, what we obtain is final results. This term look like this. There exists amplitude of one wave, amplitude of second wave, and cosinus of something. This something is called phase difference. And if we discuss this, it means what happens if you have two orthogonal polarized waves? Scalar product is equal to 0. So we have no interference. Intensity is simple sum of intensity of separated light. But what if plane of polarization of these two waves is parallel? We obtain this interference part, and this interference part depends on this cosine. And you can see it can be depending on delta. Intensity can be just sum of this, larger than sum, or smaller than sum of this. So you probably see this as you can superpose two waves, that means sum of two waves. It can be with resultant waves, and this maximum of interference, or you have not obtained any waves. This is interference minimum. So what about coherence? Coherence is connected to this part, and two sources are considered coherent if they emit waves that maintain constant phase relation. What is that important? Remember that this cosine we obtained as average. Average, for measurements, we need about a period of seconds to measure something. But waves are changed in change billion in million times in 1 second. So if you imagine that there are different two waves, difference, for example, in 1 million part, there are a billion times that the difference can accumulate errors. So if you want to measure this phase, and this is very important for interference, two sources must be coherent. What means incoherent? I already mentioned. Coherent means something like this. Coherent means that they are aligned. That phase is constant during the time. Incoherent, you have light-emitting diodes, and source for coherent is laser light. And this is the point where quantum mechanics, quantum physics enters again. There exist three processes in atoms. One process is when you, according to Bohr postulates, when you enlight by photons one atoms, and the electron is of the lower level, electron can absorb that atom and go to upper level. This energy is equally to energy of the photon. Another process is when electrons is on the upper level, they can spontaneously move to down level. And this time is average about 10 nanoseconds. And there is the third process that is proposed by Einstein. What happens if we have electrons on upper level and photons, resonant photons came during the time there is electron at upper levels. Electron moves to the down and lower level and emits photons. Photons that is exactly like photons that cause this emission. This causes stimulated emission. And what is characteristics of this stimulated emission? This photon is completely identical. When I say completely identical, it means it's clone of photons, but not clone in sense of clones in Star Wars, because clones in Star Wars are based on their genetics, and during the replication, there's some change, could be some changes between clones, but in these elementary particles, there's no difference, there's not any difference. They're completely the same. And what means completely the same? The energy, of course, is equal. That phase is equal. That polarization is equal. And of course, the direction of polarization, the propagation is equal. So quantum mechanics told us that if we have stimulated emission, we will obtain coherent radiance. How we can obtain? This is the basic for the lasers. Can you imagine this, that medium is full? You can see this is atom in ground states. And in some way, you can make some excitation of these atoms in ground states and produce a large amount of atoms in upper states. And some of atoms in upper states will emit photons. If these photons from this position find some electrons in upper states, there will be two photons emitted. And after that, will be propagate in the same direction, completely the same photons, and produce another photons if there exists some atom in excited state. And what is the most important for the laser? To keep that photons that is produced through the stimulation emission in this active medium. They produce excited atoms. And you can keep it if you put this if you put this some resonators, we put these some mirrors and put back in that direction photons, and another mirror and put back, and after 1,000,000 times you can produce these radiations with all clonated photons. And these photons are directed in the same direction. They have same polarization, same energy, and the same phase. They're coherent radiation. You can see how it's formed like avalanches form photons. And this is the reason why this device is called light amplification, because you increase number of photons. And the process is by stimulated emission of radiation. And this is the laser. How laser works? You have possibility to pump this active region and produce electrons move electrons in the upper levels, and this produces stimulated emission, and you obtain laser output. But this is not so easy, because normal distribution means that you have the largest amount of atoms in the lower level, and you have to make something in some process that you have a larger population in upper level than in lower level. And this is not equilibrium state. This is out of equilibrium. And for this purpose, you have to pump this. What is pump, for example, for helium neon laser? That means that helium atoms is in one discharge. I think that I put this. In the electric discharge, electrons are collided with helium atoms, and they are in populated states. After that, helium atom collides with neon atoms, and this is the level that is obtained in population inversion. And this is laser line that emits these red lines, 6324.7. And this is obtained in this laser. What you can see in this picture? You can see active region, and you can see two mirrors in the end. One mirror is completely reflected, 100%. This one is 98, 99. And you obtain laser light which is coherent and is useful for experiment for demonstration of interference. And I show you polarizer, how polarizer works. You can imagine this light is emitted from different photons, from different atoms. Different atoms is spontaneous process, and different atoms emit in different directions. But you focus here, you obtain this direction. But emit it's a different polarization, because spontaneous process, and you cannot favorite any of polarization. So you have unpolarized light. But unpolarized light passing through this device, which was polarizer, you obtain polarized light. I do not talk about how polarizer works, what is the physical mechanism in here, but you obtained polarized light. This is polarized light along the line of polarization. And it is polarized light, that means that electric field oscillates in this direction, and after passing to another polarized, which is oriented axis in this direction, we obtain this polarization. But what happens if you use cross polarizer? If electric field is polarized in this direction, and you put after that polarizer orthogonally with axis orthogonally to this polarizer, you have seen nothing. And if you put polarizer under some angle, you have seen something that is parallel to the polarized axis. And what happens in that situation if we put polarizer between these polarizers? This is so-called paradox of third polarizer. So we polarize this light, after that put polarizer in orthogonal direction, and we cannot observe any light. But if put polarize between these polarizers, what will happen? First, we obtain polarized light in this direction. That polarized with axis in this direction, obtain polarization in that direction, along the line. This is, of course, projection of this direction, projection of electric field on this direction. And after that, we use projection of this on horizontal. So if you put polarizer one between two polarizers, we obtain lights. In this situation, we have no lights after polarizer, put between them under some angle, and we obtain lights. And that. When you can see these polarized films. These polarized films oriented parallel, this polarized film oriented orthogonal, and this is the third under the angle. And you can see that is no black square, which means there's no any light, but there is some light. Go back to experiment, another experiment, Frey-Larragot experiment. We use this calcet to make double slit experiment, but I remind you that after that, what we obtain at the screen. When we use helium-neon laser, obtain something like that. This is overlap two spots, or something like that with green laser. And why is no interference? There is no interference because that light are mutually orthogonal polarized. And we have not seen any interference. This formula says to us there's no interference if they are mutually polarized, mutually orthogonally polarized. But what will happen if you put some polarizer bit after that, at that position, under the angle, for example, for 45 degrees? We obtain at the position that overlapped, we obtained interference patterns. And also for green light. And why we obtain? Because they have parallel electrical vectors. The parallel electrical vectors means that this interference part is not zero. And this is the reason why we obtain interference. By the way, this experiment is confirmed that, that light waves are transversal waves, because you can, if you use polarizer and do not obtain any interference, you can confirm that that light waves are transversal waves. And go back to our experiments. There one small difference between laser that we used in previous experiments and that we use in experiments I show you the movie. That is the laser resonator. This means two mirrors. In that laser resonator, it's possible to form standing waves. Standing waves, you heard about standing waves. This is like string on guitar that is anchored in these two positions, and only waves you can obtain is that is in this position is nodule of the waves. And you can observe these waves, like these waves, and all others. And similarly happens in laser resonators. So you can see this example of two waves. There fits this resonator. So there are many of these. It's called longitudinal modes. They can be lighted during the emission from the laser. You can see several of them. And what we have in our laser, we have about 2 modes. But what is interesting about these modes? They are mutually orthogonally polarized. Subsequent modes are mutually orthogonally polarized. And why that? Against quantum mechanics. Because there are several levels here exist. And light is produced by different levels. And the light that can survive, and I remind you that light is emitted only after 1,000,000 times they are passing through the resonator. So survive only these longitudinal modes with mutually orthogonal polarization. And this is the reason why we obtain something like this. Here we have only one polarization, and according to previous experiment, we have clear interference patterns. Here we have in another direction, but indeed exist 2 polarizations. But this one prevails, and we also can see interference patterns. But in this situation, they are orthogonally modes with orthogonal polarization, and there is no interference. But what is the problem? When we enlarge these interference patterns, we obtain something like this, and after that we put in distinct numbers and obtain some distribution. This is for vertical polarization. This is for horizontal polarization. And this is mutual. And what is interesting, look at this position of bright lines. And if I move back, I will go to this dark line. And you can see that position of maximum of this is position of minima of this. And what we see here, it's two interference patterns. They are close. If you have one interference, 2 interference, you close something like this. And you have no C interference. Actual interference exists. Interference is formed, but you cannot see because they are caused by phase shifting. And this is the reason why we obtain something like this. I hope, and when we mathematically sum these 2 pictures, we obtain almost exactly like we obtained in the experiment. And this is sum of 2 interference images. I hope that you understand our experiments and how we work and how we connect quantum mechanics and classical physics in one student experiment. Thank you for your attention.
So thank you very much, Professor. I think we still have time for a couple of questions. Besides Omiros, is anyone else that would like to ask something? Come back to you, Omiros. Please.
Thank you. So about the polarizers, all the polarizers shown we're polarizing light in two axes, X, Y, or the combination of the two. Can you polarize light in the third axis?
In third axis?
Yes. Or is light two-dimensional?
Electromagnetic wave is transversal wave. So you have no electric field in this direction of propagation. There no exist electric field in direction of propagation. They only exist in planar. And this is why we cannot obtain something polarization in direction of propagation. This is the nature of electromagnetic wave.
I think we've got one more question. Please, Zomiros, be quick.
I would like to ask about the double slit experiment.
Yes.
Can it be done with electrons instead of photons? And if yes, what are the differences between using photons and electrons in the results?
Actually, modern physics, quantum mechanics says that no differences. There are no big differences because when you use particles, you can obtain interference patterns. But if you think about, is possible to realize experiments in such way using some crystals? I think that it's not, because crystals is for light, for frequency and wavelength. This is designed for light. I cannot imagine that there's crystal or something like crystal that can be used to polarize electron wave. You know that electron can act in themselves, electrons can act themselves as waves. So I didn't heard about polarization of that kind of waves.
Okay, so if there is not another question, I would like once more to thank you for your contribution to this successful Balkan Summer School. And now I'd like to invite the students from Romania to present a similar, the apparatus for the interference. Please.
Hello. So my name is Mihai and his name is Marion. We are from Romania and we have a Michelson interferometer. So the Michelson interferometer is an optical device which highlights the interference of light and highlights the nature wave of the light. So you already seen how the interference works. So I'm going to show you how it actually works. So, until we create the interference pattern, the device is made from two mirrors, one source of light, and semi-reflective mirror. You have light coming this way, and it first reflects into the first mirror, then reflects into the second. As well, after the light reflected, it's then reflected back on the semi-mirror, and it reflects back right back to the mirror, and then to a screen where you can see the interference pattern. As you know, to have interference, you need two photons which have the same frequency and intensity, and it is pretty hard to create that type of photon because a source of light emits consecutive photons at different wavelengths or different frequencies. So that this device manages to create two twin photons because of the light that bounces back from each mirror. Now we will try to create the interference pattern so you can see it on the screen. Unfortunately, this is not the best type of medium on which you can see it, but we'll try our best. For you to be able to see the interference pattern, you need stability because it is very sensible, and every perturbance in the medium it's shown in the interference pattern. Yeah. All right. If you look very closely, and if we manage to keep it still, you'll be able to see that. You can see two out of the three interference patterns. I don't know how many of you can see it, but you can come closer, maybe come on the stage to see it. Are you able to see it? No. Well, come closer. If you look, you see concentrical circles. Where there is light, that means you have constructive interference, and where it's a blank space, that means you have destructive interference. At constructive interference, the waves meet at their peak, at their amplitude, and at the deconstructive interference, they meet when they are dephased. Yeah, you can see it. This device manages to create three interference patterns, two by each side of the semi-transparent glass and one inside it. Da, e întuneric așa și se vede mai bine, stai puțin. There are many circles, right? Concentric circles. Where there's no light, where it's blank, it's destructive interference, and where it's light, it's constructive interference. Of course, if we move around it, if we step, it can sense it, especially if I open the microphone. It's very sensitive to vibration. Every
mechanical wave, but it only interferes with magnetic waves that are the same frequency as it. Like if you polarize it, it won't do nothing. But if you speak in a microphone, then it will be perturbed. Usually you can use this type of machine to measure the wavelength of light, because this how you still get interference phase changes, like the vibration change. Those are the interference, those are just when you saw the interference, we interfere with the circles because this from the double experiment. Yeah, so it's different because the double experiment, first you have two sources, alright? You have only one source, but when you move the slits, it acts like two different sources, alright? It separates into two waves, and those two waves interfere. And when they interfere on the screen, you get that vertical vertical line. But here, firstly, you have one single source that diffracts into two photons, two particles, and also the source is circular, and every interference usually is circular. Like the double slit experiment, it's exception. It's an exception from the ordinary. Usually interference are circular. Right? Okay. It depends on most on how the waves interact, right? Yeah. Because at the double slit experiment you have transfer. Here you have to them. Because the source is circular, right? Mostly, that's the simple explanation. It's much more. Yeah, the interference is all around. Yeah. So, we have interference from here to there. We measure that thing, and it's like well, so you have you choose the zero that you have for which you have the same two arms at the device. Then you move the device, one of the mirrors, a very small distance, like hundreds of nanometers, right? And then you measure how many it's pulsating, right? Then you measure how the pulses change, how they change based on how much you moved it. And then you see that for let's say 100 nanometers, you have the pulsating waves move 100 steps.
Yesterday, you had your card there.
Yeah.
The light hits not the wall, not the car.
Yeah.
The distance difference.
Yeah. Yes, it affects. Yeah. What you're asking me, or what you're saying? Yeah, it does. I mean, for 10 meters arms from the mirrors to the parallel plane, then it's way much harder to calibrate it, because optics needs to be like really specific in distance. You need to move very, very, very small distances, and if you have like a big arm, then you have to calibrate the mirrors much more closely. You have to be much more attentive. That's very similar technology that uses interference in the gravitational wave detector. Oh yeah? Do you know about this? I don't know that. So they have two lasers that perfectly cancel out each other, right? But it's like kilometers long. So if a gravitational wave passes, essentially space stretches it. So they don't cancel out perfectly. And when it blinks, the laser light means one rotating wave pass. But the difficulty with this method is the actual precision. So they dig very deep so no vibration, and they have whole systems to reduce the losses. We did this last year. Yes. So the starting is wants to catch it in white light, then you have to be really meticulous when having a sense in the sense. Because in white light, you have the exact same distance or a different technique when you were, or then you get nothing. Because you have to like 1 or 2 nanometers. You had this experience. Our teacher for months. Have you done a research paper for this? Yeah, we have one where we can publish it. We did it like we had how do you call this device? Nicholson. I think we're done. Thank you very much. Thank you as well. That was very interesting.
Okay, next team on the floor, Αλέξανδρος Παπαθανασίου, George Τσαγκάρης, Γιάννης Τουρλίνης.
Opa. Hello everyone. We are a team of 3 high school students from the AFS High School. And we're going to present to you today the Stern-Gerlach experiment. Our presentation consists of 7 main units. I will start by presenting an introduction to quantum context and the historical context of the experiment. Quantum mechanics help us understand the world at a very small scale, way smaller than what we can see. It's where classical physics fails to explain things like electron behavior or atomic structure. One of the most interesting features is that it's not deterministic. Outcomes are based on probabilities. The Stern-Gerlach experiment is one of the most important experiments to reveal this strangeness. Moving on the historical context of this experiment, during the early 20th century, the atomic model was still in its formative stages. The Bohr model, introduced by Niels Bohr in 1913, has proposed that electrons orbit the nucleus in specific energy levels. However, the understanding of atomic structure and the behavior of electrons was far from complete. It was within this context that Stern and Gerlach conducted their experiment. Their work together was pivotal in demonstrating the quantized nature of atomic spin. Moving on to the second unit, which are the theoretical foundations of the experiment. What is spin? This has been mentioned on the presentation before us, but spin is an angular momentum that describes how much an object rotates in circular motion. When an object revolves like Earth around the Sun, it moves around an external point. When it spins like an ice skater, it rotates around its own axis. In quantum mechanics, spin is a particle's in-strict angular momentum, not physical rotation, but still a fundamental quantized property. Electrons, for example, have spin values of +½ or -½ which affect how they interact with magnetic fields. Particles with half-integer spin are called fermions, while those with integer spin are bosons. Now we will present to you the classical predictions of classical physics for the experiment. Classical physics would have predicted that if atoms were bar magnets pointing in random directions, the beam would deflect into a continuous range of positions. This is explained on the graph on the top left of the slide. You'd expect a blurred line of continuous distribution on the screen.
Now, let's move to the third unit regarding the experiment conducted by Stern and Gerlach and its results. The Stern-Gerlach apparatus included an oven producing a beam of silver atoms, a collimator to align the beam, and a non-uniform magnetic field and a detector plate. Silver atoms were used because they have one unpaired electron, which spin gives rise to the magnetic moment. The non-uniform magnetic field was essential because it exerted a force on the atoms based on their spin orientation. Now let's move to the surprising results. As you can see on the vector before, the beam did not spread into a continuous band, but instead it split into two distinct spots on the screen, seen in the vector 5. This was one of the first proofs that nature is quantized, and it shows that silver atoms can only be in one of two spin states when measured along the z-axis. Now let's watch a small video of describing the Stern-Gerlach experiment.
Why do scientists geek out over silver atoms and magnets? Let's dive into the mind-bending world of the Stern-Gerlach experiment. In 1922, Otto Stern and Walter Gerlach performed a groundbreaking experiment that shook the foundations of classical physics. They shot a beam of silver atoms through an inhomogeneous magnetic field, expecting a continuous spread on the detector. But what did they see? Two distinct spots. This unexpected result was the first concrete evidence that angular momentum is quantized. It's like discovering particles have their own dance moves, spin up or spin down. This concept of spin is now fundamental in quantum mechanics, impacting everything from quantum computing to MRI scans. So next time you hear about quantum weirdness, remember it all started with some silver atoms and a magnetic field.
But now, you may ask, how can these results be interpreted through the quantum lens? Electrons firstly, have intrinsic angular momentum called spin, which is a fundamental quantum property not due to classical motion. In the Stern-Gerlach experiment, the beam of silver atoms split into two parts, showing that the electron's magnetic moment can only align in two ways, spin up or down. This provided the first experimental proof of spatial quantization. That angular momentum takes on only specific directions. Before measurement, an electron exists in a superposition of both spin states. But when measured, the wave function collapses, and the electron is found in one definite state. This collapse upon observation is a core concept of quantum mechanics. Now, how can we measure spin into a new direction? If we measure spin along the z-axis and then send the same particles through a different measuring spin in the x-axis, and in the x-axis, the results are either plus 1 divided by 2 or minus 1 divided by 2. But now they're random. That's because spin measurements along different axes don't commute. They interfere with each other. This shows how measurements change the quantum state. Finally, to summarize what we've learned so far, quantum systems exist in superposition until measured. Measurement collapses the wave function into one definite state. Some measurements cannot be known at the same time because they're incompatible. And finally, the outcomes of quantum experiments are probabilistic, not predictable.
Okay, so I will talk about the relevance and applications. We didn't have access to real lab equipment, so we used simulation tools to explore how spin behaves under different measurements. For simpler visuals, we used the FET simulator, which shows the beam splitting in real time.
This is a simulation of the well-known Stern-Gerlach experiment, a landmark demonstration in quantum mechanics. It shows how particles like electrons or silver atoms have a property called spin, and how measuring that spin reveals fundamental quantum behavior. We will start by measuring particles that have spin aligned along the z-axis. As you see, all particles go up since the spin matches the measurement direction.
If we change the orientation minus z,
particles go down. Therefore, when the spin and the magnet axis are aligned, the result is predictable. Spin behaves like an on-off switch, either up or down. Now, we will measure a spin that points along x, but still use a magnet aligned along z. Now, as you see, the result is completely random. Half go up, half go down. If we auto-fire a number of them, then these numbers will be the same. When spin is measured along a direction different from its original alignment, the result is random. Quantum measurements depend on the measurement axis. Let's now fire particles with random spin direction. We get a random spread of up and down results. When the spin is unknown or mixed, measurement reveals one of the allowed outcomes. Now, we will rotate the magnet to measure at an angle between z and x. We change the angle to 50 degrees. The result is now partially random. However, more atoms will go up, but there are some that will go down. The angle between the spin and the magnet affects the probability of each outcome. This is a core idea in quantum mechanics. Measurement outcomes depend on the basis. In conclusion, the Stern-Gerlach experiment shows us that spin is quantized. Measurement is axis dependent, and the act of measuring changes the system. This simple experiment reveals the deeply non-classical nature of the quantum world.
Okay, so our simulation shows exactly what the real experiment showed. Spin measurement gives only two results. More importantly, when we measure along different axes, we disturb the system. It loses the original spin direction. This confirms how quantum measurement works and supports what we know from the theory. The concepts from Stern-Gerlach experiment are at the heart of today's quantum technologies. Spin particles are ideal qubits. They can be in superposition and we can control them. Modern quantum computers, like those from IBM and Google, use these systems. Also, spin-based electronics, called spintronics, are a real-world application of this physics. Conclusions. The Stern-Gerlach experiment shows us how different quantum reality is. Spin isn't just a number we observe. It behaves differently depending on how we try to measure it. This single experiment captures the ideas of superposition, measurement, and measurement. It's a starting point for concepts like qubits and entanglement in today's quantum technologies. We would like to thank Mrs. Vukluji for her vital guidance that she provided. And this concludes our presentation with, we conclude this presentation with these references. Thank you for your time.